So welcome everyone for this new session of the Loop Quantum Gravity Summer School. So I'm Pierre and I will chair this session. So today the first speaker is Alejandro Perez. If you have urgent questions during the course, you can ask them in the chat and I will moderate them. And otherwise there will be 10 minutes for questions at the end of the 2 hours. So Alejandro, it's your time.
Okay, thank you. So yesterday we finished, the last thing we discussed, we didn't finish the discussion, was the complexification of Minkowski spacetime. So we found that we can write, we can use an unphysical metric, which is given by the Einstein universe metric, and write it in terms of a conformal factor omega squared times the Minkowski metric, the physical metric, via this conformal transformation, and that the whole of Minkowski spacetime will fit into a compact piece of Einstein universe. The boundary of that piece is what we call infinity, and that boundary, so infinity, is where omega equals 0. So omega square is given by 4 divided by 1 minus v square times 1 minus u square in terms of the usual retarded and advanced time null coordinates. So you see that this vanishes when v and u goes to infinity. And so we saw that we could write this piece of the Einstein universe in a diagram that is a Carter-Penrose diagram that looks like this. So the whole of Minkowski spacetime is mapped into something that is compact, and the boundary defines infinity. This is I naught, space-like infinity. This is where all t equal constant surfaces end. This is scribe plus, this is I plus, and this is I minus. I just wanted to give an example of the use of this. I mean, one of the uses is to understand, to actually have these diagrams, which are very useful if we want to talk about black holes. The definition of black hole will use this compactification, and I refer to this. I will discuss this in a moment more precisely. But another advantage is that one can actually do differential geometry in this compact space, and some beautiful results can be that deal with infinity and can be expressed using the same mathematics that we use to describe things inside the space-time. And so I wanted to give you just an example, a very trivial and simple example, but it illustrates this point very well. And that is given by the following proposition, which I've taken from Wald. So this is Wald chapter 11, when they discuss asymptotic flatness. So if you have a solution of the Klein-Gordon equation in Minkowski spacetime, so let phi be a solution of the Klein-Gordon equation, so box phi equals 0 in Minkowski, with smooth initial data at t equals 0 at the Koshi surface, that for definiteness we take the t equals 0 surface in Minkowski spacetime. Smooth initial data, that means that we are providing phi and phi dot at t equals 0. And we assume that these data are of compact support. Then it turns out that phi, the solution of the Klein-Gordon equation, would go like 1 over lambda as lambda goes to infinity for lambda and affine parameter along null geodesics, and phi would go like 1 over tau square as tau goes to infinity for tau proper time along a time leg geodesic. So basically, the peeling properties of solutions of the Klein-Gordon equation are contained in this proposition. So if I draw my Minkowski spacetime very tinily here because I don't have more space, this proposition tells us that if we follow a null geodesic towards scribe plus, then the field decays like 1 over the affine parameter, which is the expected decay rate for radiation fields. And if we follow some time-like geodesic, then it decays like 1 over time squared. Once, I mean, for solutions of what? Solutions of the Klein-Gordon equation that have been given, you know, some initial data which are of compact smooth and of compact support. So this is a very nice physical property of radiation or in the solutions of the Klein-Gordon equation, which represents a massless scalar field physically. So how do you prove that? Well, we've seen that. So this is just a sketch of the proof. If phi solution of the Klein-Gordon equation in Minkowski, then one can do a conformal transformation. I mean, by looking at how the Klein-Gordon equation transforms and the conformal transformations, then you find that phi tilde defined as phi divided by omega is a solution of the following Klein-Gordon equation, phi tilde minus 1/6 of r tilde phi tilde equals 0, where box tilde means the yeah, I should have written probably box bar. So remember, we have this unphysical metric, the Einstein universe metric, which is related to the Minkowski metric by this conformal factor. So tildes means that they correspond to quantities calculated in the background given by the Einstein universe, and so which is certainly not flat, and therefore there is this scalar curvature appearing here. Now, you can actually, I mean, this will be a solution of this equation with initial data, which are, I mean, you have to provide initial data on an initial surface. And so in order to do that, you know, the t equal constant surface in t equals 0 in Minkowski touches I naught, touches this point in the Einstein universe that is not present in Minkowski spacetime because it's space like infinity. So in order for this to make sense, this what I just said to make sense, you have to extend this initial data by demanding, by saying that the initial data for this equation arches equal to 0 are at I naught. But once you have that, then there are theorems that grant that there will be a unique solution of this equation here, and that this equation and that this solution will be regular all over Minkowski spacetime. Oh, sorry, all over the Einstein universe. All over the Einstein universe, phi tilde is regular, and from there you get the result of the proposition, because now it means that you can write phi in Minkowski spacetime as omega times phi tilde. phi tilde is everywhere regular, and this, the behavior of omega as you go to infinity, tells you the result of the theorem. Remember that omega goes like 1 over 1 plus u squared times 1 plus v squared. There was a 4 here, and there is a square root. So you see clearly that if you go along null geodesics, so take this radial geodesics, then omega goes like 1 over u, or like 1 over v, depending on which of the geodesics you choose. And similarly, if you go along time-like geodesics, then you have to combine u and v to get a proper time along this geodesics, but then you see that both would be growing, and then omega will go like 1 over tau square. Anyhow, so you see that it's extremely easy to prove what is the decay rate, what are the peeling properties of solutions to the Klein-Gordon equation in Minkowski spacetime by simply using the fact that Minkowski spacetime can be mapped conformally to the Einstein universe, where infinity is a given place. So this gives you a little bit of a taste of why is it that all this technology is so important in the definition, for instance, of peeling properties of the gravitational field, and definition of charges at infinity, and for the interpretation of the physical interpretation of gravitational waves, their energy, the energy they carry, and their radiation and conservation laws. Okay, so that's only a little, digression that tell us why all this is so important. Another reason why all this is very important is because in terms of this compactification of an asymptotically flat spacetime, we can construct the definition of black hole. The rigorous definition of black hole uses this compactification. So in fact, so Minkowski spacetime, as we were saying, and here I'm going very fast and I am skipping all mathematical details. I made a mistake. So Minkowski has, infinity Minkowski has the structure, I naught, I minus, I plus, scribe plus, and scribe minus. Now, intuitively, you see that anything that would be asymptotically flat, and in fact, the way you define some spacetime to be asymptotically flat is by demanding that the structure of infinity is the same as the one you find in Minkowski spacetime. And you can do all that by demanding differential geometry properties to this compactification, to this omega that enter the compactification. I'm not going to go through all these details, but the bottom line is that anything that is asymptotically flat, in fact, that's how you define asymptotic flatness, would have infinities that look like Minkowski. So for instance, if we consider the maximal extension of the Schwarzschild solution that we discussed last time, then it will have to look like something like that. So there are two asymptotically flat regions, two regions where when you take the naive limit r going to infinity, the metric becomes closer and closer to the Minkowski metric, and therefore in each one of them there will have to be a structure that resembles, everything that is near infinity here will have to appear here too. And so infinity will look the same as in Minkowski spacetime, and so we will recover I naught, scribe plus, scribe minus, I plus, I minus, and there will be similar notions on this other asymptotically flat region. Remember that there are two asymptotically flat regions in the maximal extension. A surface like that looks like this wormhole that connects these two asymptotically flat regions. So now the physically realistic, the astrophysically realistic Schwarzschild solution will look like this, the one that we obtained from gravitational collapse. So we have some matter that formed a star that ended up collapsing. And again, there is only one asymptotically flat region and the same structure, I naught, I minus, I plus, scribe minus. And now we're ready to give the definition of black hole. So we define black hole the black hole region as the region of no escape, remember that all these are conformal diagrams, and in all these diagrams, the icon is always pointing, straight. Icons are like that. And so causality is very easy because causality is a conformal invariant notion. It's very easy we can read causality directly from these diagrams. And this gives us a very clear idea of how to define a black hole. A black hole is defined as the space-time manifold minus the past of scribe plus. So everything that is hidden by the causal structure from scribe plus. So the past of scribe plus is all this region. If you are outside this region, it means that you are unable to reach scribe plus, you're unable to escape out to infinity, and therefore you are inside the black hole. The black hole region is therefore, in this case, is what remains outside the past of so with this definition, then you would call black hole all this blue region here that is outside the past of scribe plus. And that's the perfect definition from the point of view of our previous discussion. Remember that the notion of black hole is a teleological thing. I mean, you really need to know everything that has happened in space-time for all times to be able to know where the black hole horizon is. The black hole horizon is the boundary of this region, of course. But here you see that by construction, this definition is global and needs you to know all the history of the space-time. Now, a very good question that we'll address later is, this is a classical definition. However, what happens with the black hole notion in quantum gravity? Because in quantum gravity, of course, black holes are not eternal. So black holes evaporate. And so the global structure of space-time cannot be like the one we find here at the classical level. So I'm going to come back. I mean, it's tempting to discuss this already now, but we're going to postpone this to the last lecture where we get into quantum gravity stuff. Okay, so this is the global structure of Schwarzschild, written in terms of Carter-Penrose diagrams. Carter-Penrose diagrams, of course, are somehow misleading because remember that it's just a two-dimensional description of space-time that is actually four-dimensional. So obviously there is some information that is lost when you do these diagrams, but they are extremely useful to talk about, to have discussions about black holes. In fact, I think the only clear discussions about black holes that you can have necessitate, in my opinion, the use of these diagrams. Even though some of the things you might say, sometimes, I mean, you need to do other type of diagrams, like, draw diagrams, space-time diagrams near the horizon, etc., etc. But yeah, okay, well, we're gonna do both. Now, we just studied the Schwarzschild solution, which is a static solution of vacuum Einstein's equation, spherically symmetric static. The next step is to study the Kerr-Newman solution, which represents, according to the no-hair theorem, the most general stationary black hole solution of electrovacuum, or Einstein-Maxwell's equations. So, and this theorem is extremely important because it tells us that when a black hole forms by gravitational collapse, which is something that we expect from the singularity theorems combined with the cosmic censorship conjecture that says that, the singularity theorems first say that under some natural physical conditions, then singularities will form. The cosmic censor conjecture says that once you have singularities, they will have to be inside a black hole. And now this theorem, the no-hair theorem, comes in. And I put this in quotation marks because it depends, I mean, the level of rigor. There are some assumptions in this theorem that are very good for, I mean, it becomes a theorem for theoretical physicists, but mathematical physicists will consider this still a conjecture. There are some ingredients that need to be proved, and these are very complicated mathematical problems. We're not going to worry about these things. So the no-hair theorem basically refers to a series of results obtained by Israel, Carter, Hawking. So the main results were obtained by these people and Robinson, but there are many others that actually contributed in constructing what today, and as I say, there's still activity in trying to improve this result, trying to prove the uniqueness of the Kerr-Newman solution. So basically, these results imply that the Kerr-Newman black hole that we're going to study next black holes are the only possible stationary black hole solutions of Einstein Maxwell theory. And why is it? I mean, one could say the same for vacuum, but Einstein Maxwell is very general because Einstein and Maxwell, so Einstein's equations coupled to Maxwell's equations contain, it's a very general model of matter that contains all the long-range interactions that are present in the standard model of particle physics or of our interactions. So this is enough physically to capture the idea that after gravitational collapse, so the idea that I will represent in a little diagram here. So why is this result relevant? This result is very important because it tells us that if we form a black hole from the collapse of, you know, very general collapse of matter, this could be the collision of neutron stars or a star, very massive star, that after supernova produces a black hole, etc. In any arbitrary way that we end up producing a black hole, this is not going to be a symmetric situation, and there would be a very dynamical phase here, which is very hard to describe in detail. You're going to need Einstein's equations coupled to your matter model. Even the matter models are very hard to describe in detail in a purely relativistic situation. So this is an extremely hard problem. So there will be this dynamical phase, complicated dynamical phase when you form a black hole. But if you wait long enough, so if you go up here in time for a sufficiently long time, you would expect that any deviation from stationarity would be radiated away. So you will be sending gravitational waves, matter waves away, and sooner or later the system will settle down to a stationary final state if you don't throw anything else. And this would be a stationary black hole, and the no-go theorem and the no-hair theorem tell us that that final situation will be completely described by the solution that we're going to analyze next. So that makes the following solution, which is a three-parameter family of solutions of Einstein-Maxwell theory, extremely important physically because it describes the end result of gravitational collapse. So I'm going to write the line element of the so I spent time doing this. I should have written it before. I am sorry for this. We are not going to need a lot of explicit calculations related to the metric. So this sounds like a stupid waste of time now to me, but it's too late. I'm going to write it. Well, maybe it's not a waste of time. We'll see. dt d phi, and then there is r squared plus a square minus delta a square sine square of theta divided by sigma times sine square of theta d phi square plus sigma over delta dr square plus sigma d theta square. So that's the geometry, but this is Einstein Maxwell. So we need the vector potential that describes the Maxwell field, and that one is given by Q times R over sigma times dt, the form dt minus a sine square of theta d phi. So there are several definitions that I have to give you. So the m is the mass, the gravitational mass. Q is the electric charge. A is the angular momentum per unit mass. So J is angular momentum. And we need to define sigma, which is r squared plus a squared cosine square of theta, and delta, which is r squared plus a squared plus q squared minus 2m times r. Okay, so what else should I say? This solution is stationary, but not static. Why is it stationary? Because there is this Killing field d by dt. So in these coordinates, we see it immediately. None of the metric components depend on time. And this Killing field is time-like and normalized to normalized at infinity. The metric is asymptotically flat also. And it's axisymmetric. Because there is another Killing, now only one Killing, the one we were explicitly writing before remains, so rotations around the z-axis, so to say. But it's not static. We have lost the time reversal property we had in the case of Schwarzschild, and the reason is the presence of this term here in the metric. It's not surprising that this is not static. We wouldn't like to have something that is time reversal symmetric, because this solution describes a rotating object, a rotating black hole. And if you have rotations, if you invert, if there is some natural notion of time, which there is here because space-time is stationary, if you invert this time, you expect something to change because you will be changing the direction of the rotation. So you have a ball rotating in one direction, it would just rotate in the opposite direction under this change, the reversal of time. And because rotation gravitates in general relativity, this metric cannot be time symmetric.
Alejandro, there is
Yes.
a question in the chat.
Okay.
Has the Noether theorem been proved in the presence of other external fields? For instance, so the sources of the gravitational field?
No. So the Noether theorem is not valid if you have Yang-Mills fields, for instance, or scalar fields. So if you explore the validity for general matter models, then it's no longer true. Okay. So there are more general black holes than the Kerr-Newman solution that are stationary if you include, for instance, Yang-Mills theory. Okay. but it has to be Yang-Mills theory that is not confined like in the standard model. In the standard model, the Yang-Mills fields are irrelevant for physically because, I mean, they are confined inside, you know, particles that will just be there and be important perhaps for the description of matter, like neutron stars and things like that. But once the matter crosses the event horizon of the forming black hole, then all these non-abelian gauge theories interactions are relevant, perhaps for this. I mean, there would certainly be relevant for describing dynamics inside the black hole, but they are irrelevant for whatever is happening outside because of causality. Okay. So let's look at the global structure of Kerr-Newman. And so in order to save time, I have already drawn the pictures beforehand. So this is the conformal diagram, or the Penrose diagram, Carter-Penrose diagram of Kerr. Before saying that, I should have said something. So let me go back, the page. So before discussing the black hole, very briefly, I have to say that, okay, the apparent singularity that is related with the presence of a horizon is, if you look at the metric, is where GRR blows up, and this happens where delta is equal to 0, and delta is equal to 0 for R plus or minus equal to M plus or minus square root of M square minus Q square minus A square. That was a quadratic polynomial, delta, if you look at the previous page. And these are the solutions, which of course exist only. So there is an apparent singularity that will turn out to be the black hole horizon only if M square is greater than or equal than Q square plus A square. When M square is less than Q square plus A square, there is no black hole. The conformal diagram looks like this. It's asymptotically flat with there is something like a singularity. There is a naked singularity. There is no black hole. I'm not going to discuss much this solution. This solution is totally crazy. There are closed time-like curves that go through any point. It doesn't make sense physically, so we don't consider it. Anymore in these lectures. Of course, one could discuss properties of this solution in more detail, but we don't have time to go into that. So the physical situation corresponds to this, and so the horizon is this delta equal to 0 corresponds to a divergence in the components of the metric written in these coordinates. Once more, this is just an apparent singularity. If you are smart enough as to find good coordinates, then you can actually discover this. I mean, this work was basically done by, to a large extent, by Carter in the 70s. I think in the 70s, yes, maybe before, late 60s, 70s. Sorry, I don't remember the dates at this point. Okay. Here on the left, we'll see the non-extremum case, which corresponds to M square strictly bigger than Q square minus A square. So you have a collection of, not only you have more than one asymptotically flat region, like in the Schwarzschild black hole, but you have infinitely many such asymptotically flat regions. So basically you extend, this is the delta equal to 0, one of the roots of delta equal to 0. This corresponds to the black hole horizon. This is R equal to R plus, the red lines here. The green lines correspond to R equal to R minus, okay? And the singularity is expressed here, and the singularity happens to be a ring singularity. So this can be, okay, again, so you find the singularity, but you can actually go through the interior of this ring, And this is why on the other side of this time-like singularity, which by the way, the singularity is time-like, you can space-time continuous. That's why there is this other piece, which is asymptotically flat. So these little pieces are also crazy. Inside here, you have also closed time-like curves and strange things happen. Okay. Then, of course, if you look at the Koshi surface like this one, then it has the familiar wormhole topology, like in the Schwarzschild case. Now, on the right, you see the extremal case, which is very different from this one. So this is the case m squared equal to q squared minus a squared. Now, if you look at Koshi surface like this one, then it looks like an infinite throat that never ends. So this point here is at infinite distance from space-like distance from any point on the t equal constant surface. So if you want to go all the way to this point here, then you have to cover an infinite distance. So you see that topologically speaking, I mean, the topology, it's really very different between the non-extremal black hole and the extremal one. And even though a lot of structures in this are expected not to be physical for reasons that I will mention in a moment, if we would ignore that and we would just look at these diagrams, then it's kind of obvious at this level, and this you have to take it as an heuristic statement only, because as I said, all this mathematical structure is not expected to survive the real physical situation. But you see at this level that extremal black holes and non-extremal black holes are really topological. I mean, it's very hard to imagine. I mean, at this level, there cannot be a continuum deformation of a non-extremal black hole that will end up giving you an extremal black hole. And so, to me, this is a kind of suggestion or about the fourth law of the third law, sorry, of black hole thermodynamics that says that, we'll see, and you probably know, extremal black holes have zero Hawking the Hawking temperature of an extremal black hole is 0. Here, the temperature is different from 0, and the third law says that you cannot achieve absolute 0 by a finite number of physical processes. And so this observation here seems to suggest an intuitive feature of Y. And again, this is not meant to be a proof, essentially because this is a statement about these maximal extensions that are not expected to be really physical.
There are two questions, Alejandro. The first is, can you briefly point out the topological identifications while going from the Carter-Penrose diagram to the topological pictures you show in the two cases?
I'm not sure if I understand the question. What I'm saying is, what I'm doing is I take here one surface, one Koshi surface like that, and I am telling you what happens with the geometry of that surface as I approach this point. And this is something you have to show by looking at the extremal Kerr geometry, and the result is what I'm telling you. This point here is at infinite distance from any point inside here. And when you look at surfaces of constant radius, for example, you would find that their area reduces, becomes smaller and smaller all the time, but you never reach a minimum value like here. Here you reach a minimum value, and then R equal constant surfaces start growing again. So that's what I can say about that question. I hope I am answering the question.
Thank you. Yes, apparently you do. There's another question by Deepak. He's asking, aren't most astrophysical black holes close to the extremal limit?
Astrophysical black holes are never going to be extremal. Astrophysical black holes can be close in a naive sense that how to say this? Yeah, of course. I mean, you can imagine astrophysical black holes that for which this becomes very close to m squared, and this is possible. And I think there is evidence that some of the black holes are very highly spinning. You would expect them to be highly spinning because in the black hole formation, you know, like macroscopic objects, like a spinning, like a planet, spinning planet or star, already has too much angular momentum, so to satisfy this inequality. So one of the things that are kind of expected from the gravitational collapse is that via gravitational waves and matter radiation, before you form a black hole, there is a lot of angular momentum that has to be radiated away. So it's easy to imagine that you would radiate away as much angular momentum as you can, and as soon as you have reached this inequality, then the black hole can be formed. So in some situations, or it should be expected that often you would form black holes with a lot of spin. Okay.
Thank you.
All right. Okay, so next. Did I say everything I have to say about this, guys? The physical realistic case, the physically realistic case. That's an important thing I have to say. So what of all this survives in an astrophysical situation? Okay, in the astrophysical situation, you will have matter collapsing, and matter collapsing again would occupy everything that is to the past of the boundary of the star that is forming the black hole. So we'll do that in a moment. So the past of all this infinite series of things is expected not to be present because it will be replaced by the geometry, the solution of Einstein's equations coupled to the matter that forms the star that will eventually collapse. To the future, also things are expected not to be physical. I told you that inside these regions here, for instance, again, closed time-like curves appear and crazy things happen. Okay, so the nice feature of this space-time is that when you test this space-time with fields, you find that as soon as you put some perturbations here, then these perturbations produce extremely strong effects. So they produce divergences, so they produce singularities. I mean, the perturbations diverge, are ill-behaved on R equal to R minus, which is called the Koshi horizon. The Koshi horizon is the boundary of the region where you can give good initial data, where you have a good initial data formulation, right? If you give initial data on this Koshi surface, you cannot predict what happens here, right? Because what happens here depends in part on what happens on your initial data surface, but it also depends on things that can come from other places. So as soon as you reach this boundary here, then predictability in terms of this Cauchy surface is lost. You extend the solution by using symmetry arguments, in this case, axis symmetry and so on, but really there is no initial value formulation that will tell you that space-time is like that. You have just maximally extended the solution by removing all apparent singularities that you find in your way, so that your space-time is geodesically complete. Now, when you put some fields and perturb, you look at what happens, you find that at that boundary, things become singular. So which suggests, strongly suggests, that the true singularity shouldn't be there, but rather around here, and perhaps, and this has motivated some of the strong versions of the cosmic censorship conjecture by Penrose, that states that all singularities inside black holes should actually be space-like. So the astrophysical situation looks more like this. So you have the matter. It looks very much like the astrophysical situation for spherically symmetric collapse. The matter producing the black hole horizon. Maybe I should have used a different color. Forming. So this is Scribe plus, the path of Scribe plus, and this is the black hole region. So all that complexity that we find in the maximal extension of the Kerr-Newman black hole simplifies to this. So this is expected to be the structure of a collapse of the space-time produced by gravitational collapse in an asymptotically flat context. We'll say more things about this in the last part of our lectures next week, when we go into discussion of quantum stuff. All right. So next, let's discuss some properties of the Kerr-Newman black hole as seen from the outside. So we don't need to worry about what happens inside. And so from the point of view of outside observers, then there is something very important, which is called the ergosphere. Which is defined by the region where the Killing field psi A, remember psi A is a stationarity Killing field, which is d by dt in the coordinates we're using, is what is a region outside the horizon where psi A becomes space-like. So that's the same thing as GTT being greater or equal to 0. And so maybe this is the only place where my explicit form of the metric I gave before is important. And so if you just write this equation here, you find that this happens for R, which is less than the mass plus the square root of m squared minus q squared minus a squared cosine of theta and greater or equal than R plus. I mean, the ergosphere extends inside the black hole, but we're going to be interested only about the outside. So let me do some pictures. So if this is the black hole, then the ergosphere looks like this when you look at it from the side. So this is direction of rotation. This is d by d phi, say. And when you look at it from the top, it's an axisymmetric region. You have the black hole and you have all this region outside. Now it turns out that causality, so inside this region, the time translational symmetry becomes space-like. So instead of being a time translation, it is a space-like direction. Translating in the direction of d by dt inside the ergosphere is like walking to, well, not walking, I mean walking in an acausal way, of course, walking in a space-like direction. Walking is always in a causal time-like direction, but you know, I allow my abuse of language. Okay, so inside causality here constrains you. So the light cones, I'm going to represent this by saying that the light cones are like, you know, tilted so that if you are inside the black hole, the ergosphere, you are forced to turn in the direction of rotation of the black hole. You're forced to turn in the d by d phi direction. I mean, stopping your phi naught by causality has to be different from 0. Okay. As soon as you enter this region, you're forced to turn around the black hole. And we'll talk about what it means to turn, and you'll see what subtlety I am referring to in a moment. But at the moment, it means simply that phi dot for anybody, any time-like observer inside the ergosphere must be different from 0. So this is called the ergosphere. I'm going to denote it by ES from now on. Okay. Inside the ergosphere, you're forced to turn, as we were saying. And so, but there are some natural observers that people often defined, which are called the
Just
Zamos.
a short question, Alejandro,
Yes.
about the rotation. He's asked, is it just a coordinate effect?
Yeah, let me wait until I will answer this question in a moment. It's simply saying that phi dot inside this, it has to be different from 0, okay? So from the point of view of, say, fixed stars far away at infinity, you're turning, okay? If you think of the fixed stars as defining constant values of phi, okay? So it's not a coordinate, I mean, it's what it is, it's that. But it's, okay, so just wait a second, because all my hesitation comes from wanting to tell you more, but I will tell you more in a moment.
Okay.
Okay, so there are these zero angular momentum observers, which are often evoked in the literature. These are observers that in some way are the least turning ones. They are proportional to the gradient of the function t. So it turns out that the gradient of the function t is time-like, but past directed inside the ergosphere. Well, once you know that it's time-like, that it is past directed comes immediately. So this is a little exercise, okay? So if you call this TA, then because it's time-like, TA has to be less than 0, but this can be written as TA grad A of t less than 0, which is the same thing as t acting on the function t less than 0. It means that in the direction of the vector t, time decreases. And this is what shows you that this is past directed. So what you have to work a little bit more is to show that this is actually time-like direction. And that's why, because it's past directed, if I want to define a future directed observer, an observer which is moving to the future, I have to put a minus sign and divide by the norm of this vector, so that this is a forward velocity. So these are called Zamos, zero angular momentum observers, because they have zero angular momentum. So in that sense, they are least turning. So if you compute the angular momentum of these guys, which remember is the inner product between their forward velocity and the d by d phi killing field, then you find this is proportional to psi a grad A of t, right? And this is just dt by d phi, which is 0. Okay, that's why they have zero angular momentum, and in that sense, they are the least turning guys, and they are related to other observers that I will introduce in a moment. But before, let me tell you, so these are just a few important definitions before we do some physics. Namely, we're going to talk about the Pendulous mechanism of extraction of energy from a stationary black hole. So the generators, let me define the generators, the null generators of the black hole horizon. So the black hole is a null surface, and it's generated by null vectors, which are geodesic. We'll prove that they are geodesic. Now, the horizon has to be preserved by the symmetries of the background, right? This spacetime is stationary and axisymmetric. Now we know in the case of the Schwarzschild solution, d by dt becomes null at the horizon, and so the generator of the horizon is the d by dt. Now d by dt is space-like at the horizon, because the horizon is inside the ergosphere. So d by dt cannot be the generator, but the generator, whatever it is, will have to be a combination of killing fields, because the horizon has to be preserved by the symmetries of the spacetime. So by just normalizing it by putting a 1 in front of psi a, then we define this psi has to be, we know it has to be this times plus some constant that I'm going to call omega times psi a. Remember, this is d by dt, and this is d by d phi. Now, because this is d by dt and this is d by d phi, clearly this omega here can be interpreted. I mean, if I think of this as a tangent vector to some curve in space-time, then this omega is certainly the ratio between the phi dot component and the t dot component. The ratio is nothing else but d phi by dt, and that's why it's called omega. This omega is the angular velocity of the horizon, and this chi, it's tempting to draw it like this, you know, like turning around. If I think of naively of some coordinate system where phi is phi equal constant are straight lines here, then you would draw it like that. But there are reasons for which this is not good. The reason is that this chi happens to be normal to the surface, and whenever you have a vector field that actually twists like that, then it's not hypersurface orthogonal. So it is more natural to draw this, and this is the thing I was trying to say before, but it was too early to say it. To me, it's more natural to draw this vector field chi like that. So we'll see soon that this chi, these curves here are geodesics. So these are geodesics. So these are freely falling photons, if you want, orbits of freely falling photons. So it is natural to think of them as not rotating at all, and rather to think that what is rotating is the fixed. I mean, if you were sitting there and you were looking at the fixed stars, I mean, you cannot sit there because you have to move at the speed of light, but the fixed stars would be rotating around you. So the horizon is not rotating, but the stars are rotating around you. Okay, this is kind of a Machian duality of, but it's just words at the end of the day. I mean, it's not that important. This is because, I mean, my preference for this is because chi is surface forming. So chi A is the normal, to the horizon. It generates the horizon, and so it is surface forming. So it is orthogonal to the generator of the horizon is at the same time orthogonal to the surface. Now that, so this is this vector field, obviously by construction. I mean, this is how you determine what this omega is. How do you determine this omega? You want this combination of Killing fields to be null at the horizon, and this is what is going to tell you what omega is. By the way, omega is equal to A divided by R plus square plus A square, which comes entirely from this. This is an exercise that you can do. All right, so with this structure, you can look at what happens with these vectors right outside, and you find another family of natural observers, which are not the Zamos, but they are closely related to them, stationary observers inside the ergosphere, or close to the horizon, I should say, rather close to the horizon. What are these observers? So just observe that, you just realize that you can define UA, the stationary observers, as chi A divided by their norm, chi, because chi is null on the horizon, but happens to be time-like outside, in the neighborhood of the horizon. So these are very natural observers because they follow the orbits of Killing fields. So these are people near the horizon that that would correspond to being there, sitting there. I mean, you cannot sit at the horizon, perhaps. So you're sitting there close to the horizon. This is the black hole. That is not possible, but you can imagine rather being close to the horizon with your rocket, with your starship, with your engines on, because you need to be accelerated to be there. And so you can define these observers as those which don't see space-time changing at all around them, and are approaching or close to the horizons. These observers are interesting in some situations for interpreting some of the thermodynamical laws of black holes, and we might mention them again later. So now we get to the Pendulous mechanism. So again, we need a picture. This is the black hole region. This is the ergosphere around it. And now imagine that you have a particle that you send from infinity with momentum, for momentum P0A. Now, when you get inside of this black hole, you make it split as the ergosphere, sorry. When you are inside the ergosphere, then you arrange for this particle to split into two pieces. You have a little explosion, you have a spring or something that splits the particle into two. Now, it is possible, so because you are the one who decides how to do this, I mean, you are a good engineer and you have designed your system so that inside the ergosphere, you know that inside the ergosphere, energy can be negative. Why? Because we recall energy is given by minus PA times psi A. I'm talking about the conserved quantity that means energy at infinity. So from infinity, you send the particle with a given energy. That quantity is conserved all the way, and it's always positive, of course, because at infinity was positive, because psi at infinity, it's time-like, and so this inner product is negative. With the minus sign, you get a positive. Energy is positive by definition outside. But when you get to the ergosphere, this is just a space-like translational vector. So when you are here, you can arrange your spring to kick the particle just in the right direction, so that to kick the other particle, because you split your system into two particles. So you're going to have, at this moment, a particle coming out. So one particle, PA, with PA2, and another particle. So you split the particle in two, as I said, P1A. And so you can arrange things so that P1A is such, the particle 1 has negative energy. It's quite easy. You just have to kick the particle in the direction of the killing field. Just kick the particle in this direction. And so the inner product between P1A and psi will be positive, and the energy defined by this expression would be negative. Now, why is that useful? So we'll see now that this allows you to extract energy out of the system. So let's say it again. So we go all the way to this point, and there we split the particle into two. Now, because at that point we can use the physics of special relativity at just a single point, everything, I mean, because of the equivalence principle, we know for sure that energy momentum must be conserved, and so P0A has to be equal. Energy momentum conservation implies that P1A plus P2A must be P0A. Now just compute the inner product of this with psi, and so we find, or with minus psi, and so we find that E0 must be equal to E1 plus E2. But now if you arrange E1 to be negative, then we find that E2, to satisfy this equation, will have to be greater than E0. So if we arrange the system, we can arrange now things so that the particle with energy 2 reaches goes back out of infinity. We capture this particle. We send the particle with energy E0. We capture a particle with energy E2. So we have gained energy from the system. Now, what about the particle with energy E1? So that's the negative energy particle, according to this definition of energy. And because once the particle is being created, from the splitting, this energy will have to be conserved because this is a freely falling particle and this notion is conserved according to our little lemma, then this energy will remain negative. But outside the ergosphere, nothing with negative energy can exist. So at least from there, we know that this particle will have to remain trapped inside the ergosphere. So a more detailed analysis shows that this particle will end up being absorbed by the black hole. And so that's why this picture is like that. So how much energy can we extract? Via this mechanism, this will take us naturally to the area theorem, as you will see in a moment. So imagine that, this is the horizon. I'm drawing a line at 45 degrees to emphasize the fact that the horizon is a null surface. This is the generator of the horizon, which is a null vector that we have called psi A. And now the light cone in my picture is like this. Now, the particle with negative energy that we call P1, with form momentum P1, let me just call it PA from now on, because we're going to concentrate on that one. This is a real particle that has to follow a time-like direction. So PA has to be time-like. So it will look like that. It would have to be inside. The crossing particle, the particle being absorbed by the black hole, would have to have a tangent form momentum that is time-like. So just causality tells us that the inner product between PA and chi A better be negative. The inner product between two future-directed causal vectors is always negative in our signature. So remember that. So what is that? This is, I replace what psi is, chi is, which is psi A plus omega psi A, and this has to be less than 0. Now, by definition, this first term is the energy of the falling particle minus the energy of the falling particle, and the other term gives us omega times the angular momentum of the falling particle, and this has to be less than 0, from which we conclude that omega times L has to be less than the energy of the absorbed particle. Now, if we believe again in the no-hair theorem, and we take into account back reaction, so we had a stationary situation, a particle is being absorbed, so the horizon will shake a little bit, so there would be some deviation from stationarity, but eventually we're going to reach another stationary situation. So initially we had M, Q, and J. Will end up with M plus delta M. Q will not change if the particle is not charged, and J will go to J plus delta J. So we expect that delta J from conservation of angular momentum will have to be equal to the angular momentum of the absorbed particle, and that delta M would have to be equal to the energy of the absorbed particle. So this inequality, which comes entirely from causality considerations of the particle crossing the horizon, implies that omega times delta J has to be smaller than delta M. So, well, this is a very important inequality, but before writing this inequality, I should have said something about this inequality. Look, if the particle has negative energy, does not need to have negative energy, but in the Pendulous mechanism, we want to extract energy out of the black hole, so E would be negative. If E is negative, what we immediately see is that the angular momentum has to be negative too. So which means that when the black hole absorbs a negative energy particle, at the same time, it absorbs a particle with a negative value of angular momentum in the Z direction. And by angular momentum conservation, delta J of the black hole will decrease. And so the rotational motion of the black hole will diminish, will become smaller. And the ergosphere, which exists because of rotation, will become smaller. So this is already telling us that there will be a limit to our ambition of extracting energy of the black hole, because as we use this mechanism, we slow down the rotation of the black hole, and eventually when the rotation will be equal to 0, there is no more ergosphere and we cannot do this anymore. Now, it turns out that if you look at this inequality here, you can, so there is a long history of this, but we have to do this history very shortly. If you look at the area of the black hole, which can be written as 4 pi times r, and this you can compute it yourself from the metric I gave you. Everything here is just a function, so this is just a function of the mass, the angular momentum, well, and the charge of the black hole. It turns out that this inequality here is exactly the same thing as demanding simply that the change in the area is greater or equal than 0. So I should have put here everywhere the equality. The equality is also possible, and I'm sorry, I forgot. So from the Pendulous mechanism, we find that the restrictions imposed to us to extract energy from the black hole can be easily or economically stated in this law. The area of the black hole must grow. So, and as you know, or as you expect, or you heard, this area will be related to a notion of entropy. So I can start using thermodynamical language here. So if you do this process of extraction reversibly, so if you do starting with close to extremal, so if you start from the black hole with the largest possible ergosphere, so that would be the extremal black hole, or very close to an extremal black hole, then you can show that delta E over E, the amount of energy you can get, is about 29%. All right, so by looking at this Pendulous mechanism that allows us to extract energy out of the black hole, we have discovered this interesting property. So just from causality, we found that the area of the black hole in this process cannot decrease. And then Hawking came and proved a very general theorem. Hawking area theorem that I just want to briefly mention. So if you have a black hole space-time, asymptotically flat black hole space-time, that whose Penrose diagram we said in the physical situation is expected to look like this. Now, if you consider Koshi surfaces, that represent different instants of time. So the intersection of the Koshi surface with the black hole horizon is a two surface. And so let me call these two surfaces H1 here and H2. I'm considering two different instants of time. Hawking area theorem has two assumptions. One is that there are, so you know, to prove, the theorem states, first statement, that the area of, it's very general, given the assumptions I will give you in a moment, is less or equal than the area of H2. This is not about stationary black holes. This is about arbitrary black holes defined as in terms of the causal structure of space-time, the region outside the past of future non-infinity. So what are the ingredients of this, of the proof of this theorem? The two basic ingredients are, one is that you assume that there are no singularities in the past of scribe class. So that you assume that, I'm not sure if I can, yeah, I can, that all this is singularity free, that there are no singularities outside of the black hole, and that condition is called asymptotic predictability, or strong asymptotic predictability. And the second assumption is an assumption about energy conditions. So you assume energy conditions that make gravity focusing. If you think of the Raychaudhuri equation, which we have not mentioned, and we will mention maybe next time when I prove the first law of black hole mechanics in terms of the physical process version, we are assuming that this is greater than 0. This is the Ricci tensor for all null vectors Ka. Which of course is this is valid for if you assume the weak, if you assume the validity of Heisenberg's equations with the weak or the strong energy conditions, which is satisfied by regular matter, of course. Now, but I would like to give you an intuition about that, because we have already seen this, and the intuition will be, it's actually extremely intuitive why this theorem is very hard to prove. I mean, you need a lot of technicalities to deal with the proof, but to get the intuition of why it holds is not so complicated. So think of the spherical gravitational collapse, and the only reason I assume spherical symmetry is just because it's easier to draw the pictures. It's not necessary at all to get the intuition. So you just think about it and you'll see why. So remember, if we have a spherically symmetric black hole forming, then after the gravitational collapse, there will be the apparent horizon of the Schwarzschild apparent horizon developing, right? But we said this apparent horizon is not really the horizon unless nothing else ever happens again. So assume that there is a shell of matter coming later, as we did in the previous lecture. So the geometry after the shell falls will be given by a new Schwarzschild with a bigger mass. So the apparent horizon would be outside. It would be bigger than the original green one. In fact, because of the focusing properties of this matter that fell there, these light rays that were coming, that were trapped by the gravitational field before, now they will be over-trapped. They will be focused more, and they will end up falling into the singularity. Now, what is the black hole horizon now? If I assume that nothing else happens from now on, then this would be the horizon, the last Schwarzschild. And I have to follow this back in time, right, to find the horizon in the past. And so here, this will be a surface that becomes very close to this one and then shrinks to something that looks like a So you see that the horizon I just drew here satisfies the area law, right? It's always growing in area. It starts like a point, it's growing, and then it keeps growing until it stops growing. Why? This is the area. This is the content of the area theorem. So the true horizon has to be growing. It has to be always growing in area in preparation for the matter that might fall later, and due to which the focusing effect will stop the growth, right? So this part of the horizon is growing in area because it knows, it knows in some sense that later there will be some matter falling and focusing this rays in order to make it, to stop the growth of the area. So the area of the horizon has to be always growing because it is defined backwards in time. It is always a property that depends on what will happen and continue to happen from now to the end of the world. So the area theorem is completely intuitive from the teleological definition of horizon, and I hope these pictures have helped you to convince you. So the area of the horizon has to be growing in preparation for the matter to come because of the focusing effect of matter. And if it's not growing, the matter that will come later will make it focus and make this rays collapse to the singularity and abandon the, pushing the boundary of the black hole elsewhere.
I have a question, Alejandro.
Yes.
Regarding the first assumption, how does the theorem fit in a cosmological background where you have a Big Bang and so singularity in the past?
I am sure there is some result in the literature proving that this is also true in some cosmological setup. But you have to change many things. If you're in the cosmological setup, you cannot use the black hole definition. You don't have an asymptotically flat space-time. You can still define black holes in some situations if your space-time is asymptotically de Sitter, or if your space-time is asymptotically anti-de Sitter, etc. Let's say you use asymptotically de Sitter, which seems to fit our universe. I don't know by heart. I cannot tell you where that paper is written, but I'm sure that the paper will exist. So the only thing you need is that there are no singularities around the region where the black hole is. If you have some singularities to the past, like an initial singularity in cosmology, I don't think this will ruin the possibility of a proof. Okay.
Thank you.
All right, so we are almost done. How much time do I have?
You still have 20 minutes.
Oh, okay, so we're gonna finish today. All right, so now that we have discussed the area law, which of course has a direct interpretation in terms of the second law of thermodynamics when we talk about black hole thermodynamics when we get there. So for the moment, this is just the classical property of horizons, of black holes. We talk about that. So, but there is a series of relations and laws satisfied by black holes that have a direct analogy in thermodynamics. And so the name of these laws are thermodynamical names. So the area law is the second law, or the second law of black hole mechanics. There is also a zeroth law, which is what I want to describe now, and a first law. And we have already invoked this third law that says that we cannot reach extremality by a finite number of physical processes. We did not prove it. In fact, it's hard to prove that one, but you can get convinced of its validity by looking at examples. This is very similar to thermodynamics. You never prove the third law of thermodynamics. You just show that it's that whenever you try, you fail to reach absolute zero. Okay, so the Zeroth law. I forgot to say something important. I will try to remember. We have time, so I can come back. So we have our horizon and the generator of the horizon, that is chi A. So chi A is the null normal to the black hole horizon. So chi is equal to 0 and constant all the way on the horizon. Because this function is constant, and it must happen that the gradient of this function be proportional to the normal, to the surface where this function is constant. So this has to be proportional to chi itself, and the proportionality constant, I'm going to call it -2 kappa. The reason is that if I introduce this definition, this kappa will be something very important in black hole thermodynamics. It's called the surface gravity. I introduce it that way because just by using that chi A is a Killing field, and using the Leibniz rule, from there you can prove that chi C grad C of chi A really in two steps equals to kappa psi A. And so, as advertised before, the generator of the horizon is geodesic, but it's not affinely parameterized. Instead of getting 0 here, we're getting something times chi itself. So this is the non-affinely parameterized geodesic equation, and kappa, in this sense, the surface gravity, can be interpreted as what tells us how much we deviate from having a generator which is affinely parameterized. Now, from this equation, so kappa, very importantly, will be related to Hawking temperature when we discuss quantum effects. So this kappa is the analog of a temperature. And so the Zeroth law is a statement about the constancy of, or the homogeneity of this temperature on the black hole horizon for a stationary black hole. So a black hole that is in equilibrium has a constant temperature, has a constant surface gravity, and this is the Zeroth law in analogy to the fact that an object in thermal equilibrium has a uniform temperature. Now, this is not a trivial statement. It would be a trivial statement in the Reisner-Nostrom and the Schwarzschild case, because we have spherical symmetry, so the horizon is spherically symmetric, and so whatever we define, it will have to be the same all around the horizon because of spherical symmetry. But for the Kerr-Newman black hole, the horizon is not spherically symmetric. So you can prove that kappa is constant along the generators directly from here. So proving that kappa does not change when I move along a generator is trivial. You just take the Lie derivative of this equation along chi, and you will find that, and you will prove that the Lie derivative along chi of kappa equals 0 from Lie deriving all that. If you wanted to prove intrinsically that kappa is constant when you jump from one generator to another, then this is how people actually prove this law in the first place. Then you need to do a little bit more work, and if you're interested, the details are in textbooks like Wall. But if you trust the Noether theorem, if you assume the validity of the Noether theorem, then you can just get this zero law by direct calculation. Sorry. You can also get that kappa is constant on the horizon by direct calculation, right? You just take chi, you know what chi is. You know the background geometry. You just compute this and you will find what kappa is, and you find that kappa is actually constant. It doesn't depend on theta. nor phi, nor anything. Not depending on phi, and t is trivial because of the symmetries of the space-time. Not depending on theta, it's not trivial. So direct calculation in the Kerr-Newman solution gives you the zeroth law. Now, if you want to say that any stationary black hole has a constant kappa, then you need the Noether theorem that tells you that any stationary black hole is a member of the Kerr-Newman family. Now, if you compute kappa, you're going to find, if you compute explicitly kappa, then you find that this is given by m squared minus a squared minus q squared divided by 2m which is only depending on q, m, and a. Now, why is it called surface gravity? Kappa is called surface gravity because if you consider the black hole and imagine a black hole that is not rotating, and what I'm going to say makes sense only for non-rotating black holes, but can be then understood in general, as you'll see in a moment. So if the black hole is non-rotating, then imagine that you have a mass or something hanging from a string close to the black hole, and then there will be a local acceleration of this mass, the value of the tension per unit mass that you need to put here in the string so that this mass doesn't fall and remain stationary close to the black hole. So it's easy to convince yourself that the acceleration or the force per unit mass that you have to do at infinity, A at infinity, is given by the norm of the Killing. So this is a stationary mass, so it is following the orbits of our stationary observers that we introduced before, that were defined in terms of this combination of Killing vectors. So the acceleration at infinity is given by the acceleration, the local acceleration times the norm of the Killing field, which happens to be a redshift factor. That forces get redshifted can be easily proved by doing a little exercise. Imagine that you do a little bit of work. You just displace this mass by delta L, and you assume that your string is unextensible. So that means that you're going to displace here by delta L as well. So you will do some work here, okay? Imagine that I have a machine that will transform this work into photons, and it will send all the energy in terms of photons to me up here. So the work I've done here, so work at infinity will be related to the work I've done locally here by a redshift factor. So the amount of energy that I receive here would be redshifted because all these photons will be slowed down, so to say, by the gravitational field in between. So conservation of energy arguments imply that if work is related by this redshift factor and delta L is the same, then forces are going to be redshifted, and this is how the acceleration up here is redshifted with respect to the local acceleration. Now, kappa, the surface gravity, is defined as the value of the acceleration at infinity in the limit where this point approaches the horizon. In that limit, A blows up to infinity, but chi goes to 0. Remember that chi is a null vector at the horizon, and this product is finite. So what is kappa? Kappa is the value, so the limit of A at infinity, the acceleration of gravity felt from infinity, or a particle that is approaching the horizon. And this is how it's called the surface gravity, is the acceleration of gravity as seen from infinity. And that quantity will be related to the temperature of the black hole. And this is how we call it surface gravity. Now, if the black hole is rotating, you cannot use a string, but because as we said, if you are close to the horizon, you are forced to rotate, and so the string, you cannot hold something with a string that is rotating with respect to u at infinity. But you can still repeat the same idea by using a little rocket, right? The picture of the rocket, the stationary observer that I gave you before. All right, so the Zeroth Law says that no matter where you test the black hole from infinity using this notion of acceleration at infinity, you get the same value. So now we can state the first law, which we're going to prove in the most physical way possible next time. Today we're going to prove it in the simplest possible way, and the one that is perhaps the most obscure one from the physics point of view. But it's the most trivial fashion of a way of proving it. So we assume we have a black hole. We have a an initially stationary black hole that now we perturb by throwing something in. We just throw some object like a chair. We throw a chair in, and so the black hole shakes. Now we use the Noether theorem. We wait long enough until the black hole becomes stationary again. So we will start. We start with the situation in which the mass, the angular momentum, and the charge of the black hole. This is a stationary black hole. The Kerr-Newman black hole is this. We send some matter in. We assume that this is a small perturbation, so to linear order. So a small perturbation, we expect the mass to go to m plus delta m, the charge to go to q plus delta q, and the angular momentum j plus delta j. But again, so we go from one Kerr-Newman black hole to a new Kerr-Newman black hole, if we wait long enough, from one equilibrium situation to a new equilibrium situation. Both situations are described by stationary black holes. Like in thermodynamics, we relate often states of thermal equilibrium. Now, because of the Noether theorem, we know that the initial and the final situation will be described by Kerr-Newman black holes, and we know that for a Kerr-Newman black hole, the mass of the black hole can be written as a function of the area, the angular momentum, and the charge. I mean, perhaps most obvious is to write the area as a function of m, j, and q, which is something geometric you can do in 2 seconds, right? Just calculate the area of the black hole. And I gave you the answer before, is 4 pi r plus square plus a square. Write r plus in terms of m, j, and q, and a as a function of j and m. And you have this function now, you just invert this function to obtain that one, for example. Now, because this first law relates, because of the Noether theorem, we are relating one initial Kerr-Newman solution with another one which is infinitesimally close to the initial one. We can find a relationship between these parameters by simply differentiating this. Just differentiate this function, given this function, and what you find. So this is just a simple exercise. Just take the differential of that. Can I be just dm by dA times dA plus dm by dj times dj, dm by dq times dq. And when you write this explicitly, you find that that this quantity is nothing else but kappa over 8 pi dA. This one is just omega times dj, and this one is nothing else but the electrostatic potential times dq. We didn't mention the electrostatic potential, but this is what you would expect. It's just the zero component of the vector potential in this Kerr-Newman solution, that it has a non-trivial vector potential that I wrote at the beginning. So it's the zero component with respect to the time direction given by the generator of the horizon. So you find that the amount, how much the mass of the black hole changes in this process is given by the addition of these two terms that look like work terms. This is rotational work, right? Omega times how much the angular momentum changes. This is electric work, is the electric potential times how much the charge has changed. And this third term here, which is like in thermodynamics, a weird term that, I mean, a term that does not have an immediate interpretation in terms of work and rather looks like heat, is the third party in thermodynamical relations, right? In thermodynamics, you push a piston and the work you do is not equal to the energy you gain. There is a part of the energy that goes into something that is only describable in statistical mechanics in terms of these microscopic hidden degrees of freedom, these microstates. Something like that happens with these black holes. And we have discovered this via entirely classical arguments. We will discuss this further next time, and we will see that all this is related to quantum gravity. I think that's the point where I'd like to stop.
Thank you very much, Alejandro. So now I'm going to allow the participants to unmute themselves and to ask
So how much
questions.
time do we have?
So you still have 15 minutes in total, including
15.
the questions.
Okay, so let me say one more thing, that this thing I said I forgot, and I want to mention it because it's going to be important for next time. Just only 30 seconds. What I wanted to say is that in the Schwarzschild black hole, we computed the geodesics completely. And I wanted to say that in the Kerr-Newman black hole, this can be done also. And geodesics can be integrated. It's much more complicated to integrate them via quadrature. But information about the tangent vector to geodesics, so the local information, what is the, the r dot, t dot, theta dot, and phi dot at a point in terms of conserved quantities can be explicitly written. And this is very important because as in the case of Schwarzschild, we will be able to study, to test, to probe the geometry of black holes explicitly, analytically, in the case of the Kerr-Newman black hole. How is it possible? This is because in addition to E, the energy, so given a geodesic vector, UA grad A, UB equals 0. Remember that for geodesic vectors, we have conserved quantities associated to Killing vectors. So we will have the energy, which is given by UA contracted with psi A, and this is just an explicit expression that we can write. If we write UA as, T dot D by dt. Well, I'm not going to write the whole thing, so because we don't have time, but you know what I mean. Basically, by x dot mu d by dx mu A. So all these x mu dots can be expressed in terms of conserved quantities, and this is what I want to tell you now. Because we have this equation that you can write down, like in the case of Schwarzschild. We have angular momentum, and these are the two Killing fields we have. But we also have the constancy. Pay attention. This is not really the surface gravity. This is minus UA. The magnitude of the norm of the geodesic vector that is conserved also trivially. And there is one more constant of motion, which appears by, I wouldn't say by chance, it's not related to any isometry, but there is an additional constant of motion that is called Carter constant of motion, because there happens to be something called a Killing tensor that is not at all related to isometries, and just because of the properties of this Killing tensor, this quantity is also conserved. So we have one more non-trivial component, because now we cannot go to the theta equal pi over 2 plane and forget about phi dot. Now all the 4 components of the tangent vector are important, but we have 4 constants of motion. So if we want to answer questions by probing the Kerr-Newman geometry with the test particles, we can still do this analytically. That was a statement I forgot to make when we discussed the Kerr-Newman family. And so with that, now I'm really finished.
Thank you, Alejandro. So there are already 2 questions. I suggest that you unmute yourself to ask them. The first is Putarak Jayaxon. Would you like to unmute yourself and ask the question? Putarak.
Hi, can you hear me?
Yes.
Yeah, thanks for the lesson. So I want to ask if we can use the F5 parameterization of chi to set the surface gravity to 0.
Yeah, okay. So, oops, I pushed the wrong. You can, what is it? You can, yeah, you can define a new, you can define a Ka, which is some alpha times psi A, so that Ka, so this is what you are saying, right? So that this K would be actually a geodesic, but also affinely parameterized. You can do that, but this K will not be a combination of Killing fields. Okay, so the surface gravity happens to be the deviation of the Killing generator. So the generator of the horizon, which is not an arbitrary one, is the one that is written in terms of the isometries of the space-time. Okay,
I see.
The deviation of that vector is a geodesic vector, but it's not an affinely parameterized geodesic vector. And kappa, the surface gravity, measures that. Of course, you can go to another generator, which would be affinely parameter, which would satisfy this equation. But that doesn't mean that the surface gravity is 0. Okay, surface gravity is defined in terms of a very special null vector. It's the null vector that is written in terms of a combination of the Killing fields. Moreover, also, you need to normalize the d by dt part by putting a 1 here, okay? But that's the conventional thing, because you want, yeah, that's conventional.
I see. Thank you.
Next question is by Idrous Ouzine.
Yeah. Hello, can you hear me?
Yes.
Yes, thank you, Professor, for the great talks. My questions is that we know that there is a temperatures that you just derived before, and that is derived exactly from the point of view of geometry and GR. And so my questions is that Hawking temperature is actually derived from the point of view of quantum field theory and curved background, and they both seem to be in agreement. But my question is that if we have another theory of gravity, could it be that they are not in agreement to each other, the expression, I mean?
If you have a different, you mean like a modified gravity theory?
Yeah, something like that.
Okay, so if the question is what would be the property of the stationary black hole solutions, okay? So if you really modify the nature of these solutions, if you don't really have this Schwarzschild or Kerr black holes anymore, if the geometry is different because of your new theory has, you know, changed, then I don't see any reason for having the same Hawking temperature, or not. I don't even see the reason for having a temperature at all. Right? Particle creation will depend on this background geometry, and it would be different from what you find. You know, this Hawking temperature appears when you look at particle creation by a black hole that has formed and that ends up being stationary and therefore described by a member of the Kerr-Newman family. And that background geometry is crucial in computing the details of the particle creation. Okay.
Okay, so one more additional questions that, so if there, for instance, if we derive this kind of thing from another theory other than GR, is it possible that we didn't get Zeroth Law or any law of thermodynamics of black hole?
I imagine that things like that are possible, yes.
Okay, thank you very much.
Thank you. Next question is Ariadna Ribes. I don't know how to say. Sorry.
Hi. Thank you much for the nice talk. I was wondering if the Kerr-Newman metric can actually be written in the Lightcon gauge, meaning we have the VR component is equal to 1, and then we have that all the rest are components are 0. At least analytically, I mean.
The B, which one? I don't know like that now. What is the Lightcon gauge? Say it again. What component you need to be 0?
All radial components except the VR component are 0.
Except the phi R component.
No. A V, like the V is the advanced time coordinate.
V is null. Yeah. The null. Yeah.
Yeah, exactly.
I think so. I think you can do it. Yes. I can be more definite next time. I'm too tired to think quickly. Okay.
Yeah, sure. Thank you.
I don't know. Yeah.
Thank you.
I think it is possible, right? I mean, this is. No, wait. Yeah, I think it is possible, but it's non-trivial. This is closely related to writing things in terms of boundary coordinates, right?
Yes.
This is boundary coordinates that you're talking about.
Exactly.
Yes. So there are papers about that. It's not trivial. I mean, in fact, this is a question you're asking me. I did work on that. Now I forgot when you were asking the question. So it is possible, but it's complicated.
I mean, the best I've seen is written in terms of elliptic integrals. I was wondering.
That's right. The problem is that you don't have an analytic expression of you have to integrate the geodesic equation to do this. You start from infinity, from a boundary system, and now you have to go in, and it's complicated. I think there are papers by people like Israel. Maybe this is what you're referring to, Israel and this guy, I forget now, the guy that is very famous in numerical relativity now. Okay, so sorry, I'm tired, but I also tried to do this with some collaborators in Argentina, now that you mentioned. And we did get some, in my collaborators, I think they have some recent papers about this. Their name is Moresky, Osvaldo Moresky, and some student of his. Okay.
Would it be possible for you to provide some literature on this topic?
Can you send me an email and I reply to you with the best references that I can find? Okay.
Thank you very much. Yes.
No problem.
Thank you. And so there's still a question by Zishang Wang.
Zishang, hello. Are you there?
Zishang, would you like to unmute yourself?
Yeah, I am here. So I think I'm not focused enough, but can you remind me what's the KAB in the last slides?
Which one? The one you're looking at now?
Yeah, the last slides. I'm a little bit. I forgot what the KAB refers to in the last slides.
This one?
No, the last slides.
In the last slide.
KAB. Yeah, the tensor KAB. Yes.
This is the Carter killing tensor.
Killing tensor. Okay.
It's a killing tensor.
Killing tensor. Okay.
And I will get it wrong, but it's something like, this is type D solution, and there are these principal null directions L and N.
Mm-hmm.
So this tensor is something like there is some function.
Okay.
Okay, it's constructed out of LA and A and B and the metric.
Okay.
Plus or minus R square GAB, something like that, and there is something multiplying this. I believe this is okay. Anyhow, this is in any textbook, and the algebraic properties of K are such that when you compute UA grad A of C, you just get 0 algebraically, because you get 0 because when this acts on the U's, you get 0 because this is geodesic, and the last term is going to be 0 because of the symmetries of this KAB and some property of the grade, because basically because basically this gradient of KBC is completely antisymmetric or something like that. Or yeah, I wouldn't dare. I mean, it's in any textbook.
Okay,
but it's an additional bonus conserved quantity that allows you to write all the dots in terms of conserved quantities. And the next step is to integrate these equations by quadrature, and that would give you the solution of the geodesic equations, except that the integrals you have to do, some of them are elliptic integrals, and so you don't get an expression that is simple in terms of basic functions. That's all. But if you wanted to say, if you want to talk about redshift, if you want to talk about what is the frequency, or if you want to talk about local properties of geodesics, if you want to use geodesics particles following geodesics to test the geometry, then you don't need to integrate the geodesics. You need to know what happens at this space-time point. I want to know what is x dot, what is, to compute geometric quantities such as frequencies, local energies, or whatever. And we're going to discuss some properties of this type when we try to interpret what happens in quantum gravity near singularity and things like that. And when we talk about, black hole evaporation and what we expect about quantum gravity, what we expect that quantum gravity should say about, important problems such as the information paradox. We'll try to do all that next time.
Okay. Thank you.
You're welcome.
So this is the end of this first session of the afternoon. Thank you once again, Alejandro, for your course.
Thank you, Pierre. Thank you for everybody.